Okay, we are going to do notes for Unit 4, Lesson 8. What does it look like? Where we will address the guiding question. How does the repulsion of electrons generate a 3D structure that we can model for molecules? So, on page 10, notes the 3D shape of molecules can affect the ways in which they react and interact. Valence shell electron pair repulsion theory, or VSEPR, helps to predict the shape of molecules and is based on the premise that electrons around the central atom repel each other. Electrons around the central atom are called electron domains. An electron domain can be a bonding domain where electrons are shared between two atoms, or a non-bonding domain where electrons are lone pairs. So we are going to look at these molecules and compare them. So first, you should always draw the structure out. And so we've drawn carbon dioxide multiple times, so I'm just going to quickly put it in. When we talk about bonding and non-bonding domains, it is always with regards to the central atom. Okay, so if we look at carbon, we see that it has two bonding domains. Now, double bonds are only still shared between the same two atoms, so that only counts as one domain. Even though it's two bonds, it is one domain because it is between the same two elements. So then here we see we have two double bonds, that's two bonding domains. There are no lone pairs on carbon, so there are 0 non-bonding domains on the central atom. Shapes are always created around the central atom. And so if we were to draw the shape, it would look like that, and it would have a bonding angle of 180 degrees, because that's from one bond to the other is 180. If we looked at CH2O or formaldehyde and drew it, we would see that it looks like this. So if we look at the bonding domains, we see that there are two single bonds and one double bond for a total of, not two, wow, 3 for each region where bonds are occurring. There are no non-bonding domains, so when we draw it, it's just going to have 3. And so that is trigonal planar, and the bonding angle here is 120 degrees. So it looks like a triangle, but it's planar because it's flat. Our next one is CH4. And so that is 4 bonding domains, no non-bonding. And so when we draw it, in the activity, it used a wedge going one way and another. You don't have to do that as long as you attempt to draw it with perspective, so it doesn't look like it's flat. The bonding angles for these were 109.5 degrees. Next, we have ammonia, which is NH3. So we draw our H's, and we should see that there's a lone pair on nitrogen. So we count our bonding domains, which is 1, 2, 3. And then the lone pair is one pair, so that is one non-bonding domain. So when we draw it, since it adds up to 4, it should look similar to the tetrahedral, but we're going to swap one of them out for a pair of lone pairs. So we'll draw the bottom ones for the hydrogens and then stick that on top. It is pyramidal or trigonal, because there are other pyramidal shapes that we aren't going to cover in this class. Trigonal pyramidal because the base of it looks like a triangle. All good? Finally, for water, when we draw it, a lot of the times we'll draw it so it looks like this, correct? And we might say that this is linear. But what do lone pair electrons do? They bend stuff. So it is still, we have two bonds, or two bonding domains, and two non-bonding domains, so two pairs of lone pair electrons. So it still adds to 4, so we're going to still use the tetrahedral shape. But 2 of those are going to become lone pair electrons. So this is now, and I'll zoom in, bent. Whereas trigonal pyramidal had a 107-degree bond angle, this has a 104.5 degree bond angle. So it is bent. It was a line, like we see it drawn with our Lewis structure as a line. But when we draw its 3D shape, we see that that line has been bent by the repulsion caused by the lone pair electrons. Yep, bonding and non-bonding. Mm-hmm. Yeah, or 1 and 2. Like, there's a couple where it could be like 1 and 2, but you'll see like it looks like it could be linear, but it's got 2 bonding domains and there's lone pairs on it, and lone pairs bend things. Like ammonia, NH3, looks like it could be trigonal planar, but it's got a lone pair on there. It makes it no longer flat because it's going to push on those bonds and it'll pop up like a pyramid instead of being flat because they all repel. That's the big idea for VSEPR theory, is that electrons in bonds and in lone pairs repel each other to give a 3-dimensional shape. And the bond angle is much larger than 90 degrees. Sound good? Anybody need me to zoom in on these? Okay. So these 3D shapes are generated to create as much space between electron domains, both bonding and non-bonding, as possible. And this minimizes the repulsive force between electrons. When looking at how molecules react or behave in real life, drawing Lewis structures, so what we've been doing until this point, is not sufficient. Granted, it's only been like a couple days, but our early stages is not sufficient to describe what's happening. You need to also account for the shape of the molecule. And we're leading into that because when we come back from break, we are going to look at intermolecular forces and do a glitter lab. We can combine the shape and Lewis structures, and all you would do is on these, instead of writing the circles, you could write the element symbols. Boop, boop. So like this one. So I'm combining the shape and the structure to kind of make it look like perspective. We're riding the struggle bus with that one. Okay, so at the bottom of page 10, please answer the guiding question in 2 to 3 sentences, and thank you for tuning in.